Today I would like to introduce two papers regarding to the topic inductive link prediction. And then the first paper I would like to present, it has the title Link Prediction Based on Graph Neural Networks. And then this paper is published in Neurops 2018. So the task of this paper is trying to do the link prediction. And then the link prediction problem in networks usually describe the task that given an incomplete network, we would like to predict whether two nodes are likely to have a link or not. And then they have many applications. For example, it can be applied to social network to predict the friendship relation among two users. And then they can also be applied to biological networks to predict the interaction among proteins. And then one of the most traditional methods for the link prediction task is trying to use the heuristic method to predict links. So usually trying to calculate a proximity score for each pair of nodes. And then some representative methods include common neighbors, jackpots, preferential attachment. And then all of these methods have very good performance on link prediction, and then they're easy to calculate. Also, they have very high interpretability. And then the most important part is that there's no chaining required in order to calculate this score. So next I will introduce several heuristics based methods in order to illustrate how they predict links among nodes. So first of all, we will use the gamma x to denote the neighbor set of node x in the graph. The common neighbor heuristics trying to calculate score of two nodes by using the number of their common neighbors to define it. So the basic idea is that x and y are likely to have a link if they have many common neighbors. So it is a first order heuristics, and it needs only one hop neighbors to compute this score. And then another first order heuristics based method is the preferential attachment heuristics. And then the basic idea of this method is it trying to predict x and y will share a link if x. So the basic idea is that x will prefer to connect to y if y is popular. So we can observe that this method will also involve only one hop neighbors. So it is the first order heuristics method. And then for the second order heuristics method, one of the representative method is the dynamic ADA heuristics. So the basic idea of it is it trying to weight the common neighbor of two nodes, and then it will trying to make the popular common neighbor to contribute less when it calculates the score. And then we can observe that this method will involve two hop neighbors. And then so we call it the second order heuristics. And then another and then beside the first order heuristics and the second order heuristics, there are several methods related to high order heuristics. One of the classic method is the Kewei index. So the basic idea is that it will sum all works between X and Y, and then each works will discounted by beta power L, and then here beta will be smaller than 1. So it is a discount factor, and then L is the length of a work. So the basic idea of the case index is that it's trying to count all the works, all the walls between X and Y, and then it's trying to make the longer walls contribute less. And then another common used high order heuristics method is the rooted page rank. So this is like a very common use method. I thought most of us will be very familiar with it. So the basic idea is that we will let the pi x be the stationary distribution of a random walker starting from X, and then it will randomly move to one of its neighbors with the probability alpha, and then it can also return to X with probability of 1 minus alpha. So so this kind of rooted page rank is also a high order heuristics method. We need to know the entire network, and then iterate until converge in order to achieve the stationary distribution. And then so after we introduce this common use heuristics method, we were trying to point out actually they will have some drawbacks. First of all, because these heuristics trying to handcraft the graph structure features, so it cannot apply to general graph, and then it will have a strong assumption on link information. So it also limits its generalization ability. And then so in order, however, as we point out before, one of the main advantage of the heuristics method is that we can see that they calculate the score to define the proximity of two nodes by only leverage the structure information of the networks. So there's no need to training in order to predict the link, which is good and computational efficiency. And then we would like to leverage the advantage of the heuristics method. At the same time, we don't want to specify one of the heuristics method in order to predict link, because we do not have enough background knowledge to know which is the correct assumption on link information mechanism. So the author trying to propose a framework, SEAL. So the basic idea of the SEAL is that it's trying to automatically learn the general graph structure features, and then it do not hold any assumption on network property at all. And then they show that their proposed method can achieve the state-of-the-art link prediction performance based on the graph neural network. So here is the framework of the SCAL method. So the basic idea here is that given the entire graph, first of all, we're trying to extract the enclosing subgraph around the target node X and Y here, denoted as A and B. And then with this extract enclosing subgraph, we can calculate the heuristic score to determine the proximity of the two nodes A and B, and then we can predict whether there will be link among them. And then here is like the basic idea. We can observe that with this example, in order to predict whether there's link among A and B, we can extract a small subgraph from the entire graph. And then we can see that so there are many common neighbor or higher order interaction among A and B. So they're likely to hold a link. And then in order to determine whether there's link connect C and D, we can extract another subgraph surrounding C and D, and then we can observe that C and D do not have many direct or indirect interaction. So they might it will be less likely for them to connect with each other. And then
can I have a question here?
Yes.
So how big the subgraph is? Like it's just the equal network, or?
I'll introduce how can we extract this enclosing subgraph in the follow section.
Oh, okay.
So maybe we can, yeah. So that is like the basic idea of the proposed SCAL framework. So next, we will introduce the detail of the SCAL framework. This framework include 3 steps. So for the first step, we were trying to extract the enclosing subgraph as shown in these slides. And then in the second step, we were trying to construct the node information matrix in order to indicate the structure information of each node. And then the final step is we will use GNN to learn an embedding for each node in order to represent, in order to encode the structure information around them. So first of all, we would like to show how can we extract the enclosing subgraph. Here for the enclosing subgraph, we will define it as following. So for a graph G given two nodes X and Y, the edge hope enclosing subgraph for XY is the subgraph induced from G by the set of nodes which is the edge hope neighbors of X or edge hope neighbors of Y. So so basically the enclosing subgraph describes the edge hope surrounding environment of X and Y. And then is this part clear? So basically, we will the user will specify how large its edge is, and then based on the based on the value of edge, we were trying to extract the edge hope surrounding environment of the node X as well as node Y. And then after we extract this subgraph, the next step is that we will trying to construct the nose features in this belongs to this subgraph. The purpose of the nose structure label is to use different labels to mark nose different rows in an enclosing subgraph. So here, in order to achieve this goal, actually we need to make sure we can complete the following two sub-goals. The first sub-goal is that we have to design a mechanism to identify the center node X and Y. Because they are the target nodes we're trying to predict. And then in addition, we also want to ensure that nodes with different relative position to the center node X and Y can have different structure importance to the link. And then this part, the node structural label is pretty important because without the node structure labels, DRNL will not be able to tell where are the target nodes and why the nodes with different relative position to the center nodes are different. So in order to achieve this goal, the author proposed a mechanism, double radius node labeling. So here I give an example to illustrate how this double radius node labeling works. For example, we have two target nodes. We denote them as X and Y. And first of all, we will assign label 1 to both X and Y to indicate they are our target node. And then for any node I with radians dix and the diy equal to 1 and 1, which means that this node I is the neighbor of X and it also is the neighbor of Y. We will assign the label 2 to it. And then for the node with radians 1, 2 or 2, 1, it will get label 3. And then for the node with the radians 1, 3 or 3, 1, it will get 4. And then the nodes with 2 and 2 will get 5. And then the node with 1, 4 or 4, 1 will get 6. So by observe this example, we can see that basically the idea to assign the label is that if the radius, the sum of the radius have smaller value, then it will assign a smaller label. And then if two radians have the same sum, but they will have different value. For example, 1, 3 and 2, 2. Both of them have the sum of 4. Then in this case, we will assign the label. We will assign smaller label to the rate for the radians whose product will be smaller. And then we will assign the higher label to the nodes whose radian whose product of its radian will be bigger. And then so basically this node label mechanism trying to satisfy the following property. So if as we just discussed, so by using such mechanism, we can ensure that each nodes with different radium can have different labels to distinguish them. And then with this, after we getting the label of each nodes, then we will use their one-hot encoding vector to construct their information matrix X. And then by concatenating each node's embedding or attribute value to its corresponding role in X, we can also make the SEAL framework learn from all type of features. That is like how we can construct the node information matrix. And then this node information matrix basically will include two parts. The first part is the one-hot encoding to represent the label of each node. And then the purpose of this part is trying to indicate the structure information of each node and trying to distinguish different structure role of each node. And then in order to construct the node information matrix, another option is that we can also include the node's embedding or attribute vector in order to include more external informations. And then with the with this node information of each nodes in the extracted enclosing graph, we can apply a GN to learn the embedding or to update the embedding of each node in this enclosing graph. And then after that, with the update with the learned embedding by the GNN, we can learn a scoring function to indicate whether there is a link among two nodes or not. So that is like the basic idea of this framework. And then we can see that as long as we can set the edge hope, we can set the edge parameter when we're trying to extract the enclosing subgraph to be bigger than the edge, to be bigger than the 2. All first order and second order heuristics can always be learned from the local enclosing subgraph. But how about the high order heuristics method? Because all of these higher order heuristics method trying to leverage the entire graph information to predict the link of two nodes by using only the by using only a subgraph of the entire graph. Whether we can still capture the high order heuristics using the SEAL framework, it is a question. So the author answered this question by propose gamma decaying heuristics theory. So here, this theory indicates that this theory defined gamma decaying heuristics as the following form. So the gamma decayed heuristics for a pair of nodes x and y can be defined as here, and then the L represents the length of the walk between x and y, and the XYL is the score of the pair of node x, so x and y, by consider only the walk with length L between x and y. And then the author shows that a wide range of the high order heuristics can be unified into a gamma decaying heuristics framework. These higher order heuristics method including case index, root, page rank, and sim rank. So basically, all these methods can be written in form of the gamma decaying heuristics. And then the author also shows that under mild assumptions, all gamma decaying heuristics can be well approximated from local enclosing subgraph. So even though we do not have the entire network, because we only extract a subgraph, we can still, this subgraph can still capture most of the information for this higher order heuristics method. And then the approximation errors will decrease exponentially with the subgraph size. Which means that by only extract a small subgraph, most of the higher order, we can still like capture most of the higher order information. And then I didn't show the detailed proof here because like for each different method, it will trying to transform it into these formats, and then the proof how they works. So I don't think I have too many space to show all of them. So I only list the main result here. And if you are interested, you can try to find the paper and read the detail of this proof. And then the reason why I'm trying to introduce this paper is that I thought the idea of this paper here is interesting, because unlike because its main idea is that although the DRNL has the ability to propagate the neighbor information, to propagate and aggregate one's nodes in neighborhoods information. However, during this propagation, actually we will lose the structure information of each node surrounding the target node. So the basic idea of this paper is that actually, in order to distinguish the nodes with different structure importance surrounding the target node, we can define the labels to distinguish their structure roles. And then by leverage this labels by regarding these labels as the features, and then aggregate these neighbors information. We can keep like the exact structure information around a target node, and by doing this, we can enable the GN to capture as much structure information as possible. And then inspired by this idea, another paper, inductive relation prediction by subgraph reasoning, is published in ICML 2000. And then so the basic idea of this paper is that it's trying to do the relation prediction in knowledge graph, and then basically the link prediction in knowledge graph is still trying to complete the existing knowledge graph and infer the missing links in this knowledge graph. And then it will have many applications in e-commerce or material science. And then but most of current knowledge graph, most of current methods for knowledge graph link prediction can only handle transductive relation predictions. So here, what do we mean by transductive relation predictions? We give an example to illustrate it. So for example, we have a knowledge graph as shown in the slides. This knowledge graph can be regarded as the training graph. And then with this training graph, in transductive setting, we were trying to predict the missing link in this training graph in order to complete the knowledge graph. And then in this scenario, we can see that all the entities in this knowledge graph has already been observed in the training graph. But only the only missing information is some of the link among these nodes are missing. And then currently the most commonly used method is the embedding based method. So the basic idea is that they're trying to encode each node into a low dimensional embedding, and then for example, the representative methods include trans E, rotate E, and then with this embedding, they can use this embedding to predict the link, between two nodes by using the scoring function defined in different methods. But the embedding-based method have the main drawback is that it cannot make prediction on new nodes. As we discussed before, by using the embedding-based method, in order to predict the link between two nodes, first of all, we should have the low dimension embedding for each node. And then if we do not have the embedding of the new node, there's no way for us to predict which nodes will have could have the link to it. So however, most of the scenario in real world is not transductive but inductive. For example, or we could have such knowledge graph as the training graph, but when we're trying to conduct a test, when we're trying to predict the downstream task, usually we will have like some other newly appear node which need to be handled because the graph is usually involved, and then with when the time increase, then many new nodes will appear, and then it will be better for us to be able to handle this newly occurred node. And then also another scenario is that we may trying to learn the information from a training graph, but we have to transfer it to entire new test graph in order to make the prediction. And then this entirely new graph have like a totally different set of nodes compared to the training graph, but they might share the same underlying structure. And then if the model is smart enough, it should be able to learn the underlying structure and transfer the knowledge to the new test graph in order to predict the link. So so based on these requirement of the application, this paper trying to solve the task of inductive learning use GNN, and then the most important idea here is that given a knowledge graph, actually it will contain some information in the form of logical rule. For example, here in this knowledge graph, by observing this knowledge graph, we know that actually we can have such logical rule, and then this logical rule just trying to describe that if X is the spawns of Z and Z lives in city Y, then it is reasonable for us to infer that X will also live in city Y. And then this kind of underlying logical rule actually is already contained in this training graph. And then this this logical rule actually is entity independent, but they are structure dependent. So the idea of this method is trying to learn the entity independent relational semantic by mining such knowledge from the training graph. And then also another advantage of their proposed method is that compared to existing works which trying to mine logical rule, their proposed method is extremely parameter efficiency, which is like good and can make the computation to be more fast. And then the basic idea of the proposed method is inspired by the first paper we just introduced. So the basic idea is that it will trying to apply the GNN on the subgraph surrounding candidate edge, and then as like explicit rule induction is usually challenged. So instead of trying to extract the logical rule explicit. They just trying to avoid the rule induction, but only capture the latent information within the parameter of the model. And then in order to achieve this goal, their proposed model is ensure to they trying to define a mechanism which can ensure the model is expressive enough to capture logical rules. And then
so Vivian, I have a question. So I try to understand the flow here. So yeah. the whole title of this talk, right, so it's about inductive link prediction.
Yes.
So for the first work, actually I didn't see why it's called inductive. And for the second work, I didn't see why it is related to link prediction, because somehow you try to do this rule extraction.
I see. Yes, so for the, sorry for the unclearness. So, so for the first paper, as we just discussed, the basic idea of this paper is trying to, so this paper is inspired by the heuristics method for the link prediction. And then as we know, the heuristics method for the link prediction just trying to leverage the structure information around the node to do the link prediction, which means that even though we have a new node, as long as we know is surrounding links, we will be able to predict its underlying structure. So that is like so basically this link prediction based graph neural network, the goal of it is not trying to do the inductive link prediction, but it is just the second paper is inspired by the first paper in order to achieve this goal. And then the second paper is and then for the second paper, for the second paper, the basic idea is trying to solve the task of the link prediction in multi-relational graph. And then in order to achieve this goal, the basic idea of it is that so it first of all it will mask the link as the first paper trying to do, and then it will use the surrounding edge hope node environment of the target node X and Y to construct a subgraph, and then based on this subgraph, by encoding all the information in this subgraph, it will trying to use this information to predict the link among the X and Y. And then because all this information in this graph is the information in this graph only related to the structure information. So basically what they're trying to do is that they're just trying to encode the latent pattern of the latent rule pattern of the knowledge graph in order to conduct a prediction. So that is why they can be applying to inductive setting. And then here, the inductive setting, we are talking, for example, for example, here is the inductive setting we're trying to solve. And then we can observe that even though we train the graph, we train the model in a training graph. And then this training graph do not share any entity with the test graph. As long as we know the underlying rule contained in this training graph, we can will be able to predict the link in the text graph. So that is like the basic idea.
So in other words, the first paper, it does not explicitly discuss whether it's going to be inductive or transductive, but
yeah.
But
yes.
by nature, they can handle this inductive reasoning, right?
Yes.
So
yes.
That's why.
So the first paper can be regarded as like the paper inspired the second paper.
Yeah, but I guess in your flow, I think you are more interested in the knowledge graph reasoning. So I guess you first read the second paper, and then you realize that actually they rely on the first paper. So that's why you want to
yes.
in this order.
Yes.
Okay.
Yes. Yes.
Then
yes. So the first of all, I just like interested in the second paper, and then I realized that the second paper is highly relying on the first paper. So I thought before I introduce the second paper, it would be better for me to introduce the first paper.
Okay, not necessary. I think, yeah, it's also good that you can motivate people using the second work, because I think the problem itself is more interesting, right? And then probably you can discuss the challenges and saying that, oh, actually inspired by an early work, and then you can spend some time to introduce that and then come back. But then for this,
yes. Sorry.
For the second one, you mentioned the logical rules a couple of times, but I'm not quite sure like how the logical rule will play a role in this relation prediction. Is that going to be some input from users, or is that going to be some intermediate results?
No. So basically, the logical rule can be regarded as the underlying information.
Kind of a hidden pattern, right?
Yes, the hidden pattern indicates why the training graph can construct in this way. Yeah. So in order to solve the inductive setting, the basic idea is that as long as we can capture this hidden pattern, and then we can transfer this hidden pattern to a new graph, even though we do not observe the entity in the new graph, we can still do the prediction following this hidden pattern.
Okay, probably can keep going because I still didn't quite get the meat from this paper yet.
Yes, sure. So next we will introduce the idea of the second paper. So the idea of the second paper include three things. First, it will trying to apply the DRNL on the subgraph surrounding candidates edges, and then the second, as like learn the logical rule explicit will be a challenge task. So instead of learning them explicit, it's trying to avoid learning the rule directly, but learn the hidden pattern and then store them in the parameter of the model. And then the third idea is that we have to ensure the model is expressive enough to capture the logical rules. Now I will introduce like the the detail of the framework. So this as this paper is inspired by the first paper, so similar, it will also contain three steps. So the first step is that it will trying to extract a subgraph around the candidate edge. And then the second step will be it will assign the structure label to the node in this subgraph. And then the third step is that it will trying to run the GNN on the extracted subgraph in order to learn the embedding of each node. And then
a question. So for the first paper, they actually somehow, once we have a target edge, right? So we kind of label each node based on the kind of shortest distance of that node to those two nodes, right? And
yes.
then they turn that two numbers into one label. And it seems yes. In this case, they didn't do that transformation. Because yes. The reason, I guess, is like in the first case, it's kind of undirected network. So that's why there's some sort of symmetry among that edge, right? But here, that symmetricness does not exist. So in other words, a node, right? Yeah, with shortest distance 2 for the first node and shortest distance 1 to the second node, it's going to be different from the other case 1 and 2. So that's why they don't want to map that into a single number. So they want to keep the original pair of distance here, right?
Yes.
Okay.
Yes, and then I thought, yes, I think the main reason is because like when we consider a logical rule, actually the logical rule will have directions, and then in a logical rule, the relation xy r1 x the triple r1 xy will be different from the triple r1 yx. So if we cannot distinguish the difference between R1 XY and the R1 YX, we are unable to learn the rule correctly. That is the reason why they no longer use the same structure label mechanism as the first paper trying to do.
Yeah, and also it's related to the kind of using anchor nodes to assign positional encoding to those other nodes. But here, of course, the anchor nodes are dependent on the target edge, right?
Target, yeah.
Yeah, but in other cases, it's just those anchor nodes could be any anchor nodes. Mm.
Yes. So the idea of this two paper is like similar to the anchor node, but just the difference is that because the downstream task is the link prediction, so the anchor node is pretty we can specify the anchor the anchor node here is like a limit into the target node we are interested in. Mm-hmm. Because we are not interested in learning the general embedding of the whole graph. Instead of we just want to know what will be the relation between two target nodes given their surrounding subgraph structure.
Yeah, the next question is like you keep talking about this logical rules, but I still could not map that to the current graph. Mention that.
Yes. So here for the logical rule, actually we can, for example, in this example, we can observe that a logical rule can be regarded as a path in the knowledge graph. And then the ones we can observe, for example, this can be found in this path. And then as long as we can observe this path, we can predict that there will be a link connects the entity X and Y. And then this link is specified by the head relation of this logical node. So basically, a logical rule can be regarded as a path pattern appear in the knowledge graph. Then this by using this by using the similar path appear in this knowledge graph, we are able to predict the head relation among two nodes following.
Okay,
this.
yeah, so
Yes.
I think as stated in the first paper, right, so there are many heuristics, but if you look at those heuristics, essentially it can be summarized into a unified form, which means that
Yes.
if there are some sort of paths connecting two nodes, then more likely there's going to be a link between them, right?
Yes.
But for the first paper, I think the main difference is like it's kind of homogeneous network.
Yes.
We don't have to differ the type of links there. But for the second one, right? So of course we still have paths, but if you look at the path, then for example, for the length 2 path actually means quite differently because it can be concatenated with different types of relations.
Yes.
So now I understand, okay, each path is corresponding, or each closed path is corresponding to a logical rule. The body part is corresponding to that path, and the head part is corresponding to the target relation that we're going to predict, right? But then how do they handle the heterogeneity for those relation types?
So as we just discussed, so the first paper is trying to handle less challenging task compared to the second paper because the scenario is the homogeneous network. So as long as there's a link, so we just regarding all links as the same thing. So here, what we're trying to learn is the multi-relation graph. So in order to handle this multi-relational graph, actually, we will introduce the similar as the RGCN. We will introduce relation specific transformation matrix in order to capture the information information from different relations as well. And in addition to that mechanism, we will also use the attention to weight the information coming from different neighbors in order to represent the different role of different relations when we're trying to do the propagation. So so maybe we can like first introduce the whole framework, and then we will show that how this order adapt the first paper in order to handle the multi-relation scenario in knowledge graph. So so this this framework, so in similar as the first paper, this framework also contains 3 parts. So the first part is that it will first extract a subgraph around the candidate edge, and then it will try to assign structure labels to node, and then it would run GNN on the extracted graph. And then now we will introduce each step one by one. So for the first step, the idea is still similar. So given the target nodes U and V, in order to extract the subgraph around them, the idea is that we will let the NKU and the NKV be the set of nodes in the K-hop neighbor of two target nodes. And then we will use the overlapping of NKU and NKV to construct the subgraph. And then with this extract subgraph around the candidate edge, the next step will be that we will trying to assign the structure information to node. So for still similar as the first paper, for each node I in the subgraph around node U and V, we will label it with the tuple DIU and the DIV. And then here, DIU denotes the shortest distance between node I and U without counting any path through V. And then this label will capture the structure position of each node with respect to the target node X and Y. And then as we just discussed, instead of using the sum of the tuple to construct the label, here this paper will use this tuple, will concat the tuple in order to construct the node feature. The basic idea is very simple because here in the knowledge graph, the direction of the node is pretty important. As we know, like an example of the knowledge graph here will be example logical rule is shown in this example. And then we can see that if we switch the position of X and Y, and then we switch the position of X and Z, actually this logical rule will express totally different meaning. And then obviously it will no longer be reasonable. So in order to avoid such mistakes, we need to explicit distinguish the direction of the links. So they use they trying to concat the labels of the tuples in order to represent the node. And then after assign the structure label to the node, we already construct the feature associated with each node in the subgraph. And then with both the structure of the subgraph and then the feature and then the node feature of each nodes in this subgraph, now we will try to run the DRNL on the extracted subgraph in order to calculate the score of the triple URTV given the extracted and the labeled subgraph around the target nodes U and V. And
I still have a question, like about how you label them, like on the previous slides.
Yes.
I kind of understand that in terms of the direction, right? If you just one hop away, right, then very clear for the better. If some node is 2 or 3 hops away, right, then how that direction going to be?
For example, this node is like 2 hops from the target node. The target node is the red here. And then we can see that this node, the shortest path between this node and the target node X is 2 hops. So we will represent the first number of the tuple as the 2. And then we can see that this node is 1 hop neighbor of the target node Y. So we will represent this number as 1 here. And then this number 2 and Y finally will be transferred into a 1 hot encoding vector.
So basically you just, in this case, just the direction between those 2 target nodes that you want to distinguish, right? But but the directional information of other node with respect to the target node, you don't distinguish, right?
Yes.
For example, that 2, right, is just 2 hops away. You don't encode like what's the direction of the relations between on those 2 hops, right?
Yes, we do not like include such information. It only include like we only know that how far away of this node from the X and how far away of this node from Y.
But when you use, because then the information, the node feature does not include that any of those directional information of those edges, right?
Yes.
Then when you learn the next step, it will still, I mean, that information is just got lost?
I don't think that the information will get lost. So sorry, I just want to clarify. So what kind of information you are trying to say here?
It's because you do have the directions on those edges, right?
Yes.
And the relation type. So are those information will be incorporated when you learn the next step? I think you learn some embedding, right?
Yes.
Maybe you will talk about that, but that's my question, because seems if you just using those node features, right, for the next step, then a lot of information are going to be lost.
Yes. So at this stage, we do not include the relation information as well as the So when we're trying to design the DRNL architecture, we were trying to include those information in order to ensure that we know.
So later you will.
Yes. Later we will discuss how we can incorporate other information into the learning.
Yeah, I think I have a similar concern as well. I just fear, if you look at this, right, so they kind of want to do this positional encoding, but this network or this graph, right, is more complicated than the previous graph. I fear they are doing this sort of encoding, just lose lots of information, right? Potentially, for example, what kind of path? We only know, okay, there's a path with length 2, but what path is that? This sort of information is completely gone, right?
Yeah, but so let's consider the basic idea of how they define the GNN is inspired by the RGCN. So let me consider how, if in this case, how RGCN trying to do. So for example, we would like to include the relation specific information into the learning. Then how we can do? One straightforward idea is that we will assign a different matrix to different relations. And then by applying this relation-specific matrix, we can we can transform the original features of the node into another space, and then this space has already included the relation specify information, right?
Mm-hmm.
Yes. So by trying to trying to use other relation-related mechanism, actually we can include.
I guess here they just want to add some additional features to the node, but then afterwards they're going to use RGCN to take care of those different.
Yes.
So
the base. Yes. So the basic idea of why they trying to create the feature of the node is that they just trying to assign the feature to each node, and then this feature can distinguish different node by capture their structure related information.
Yeah. So here I have a question, right? So
yes,
how effective this new feature is, because even without this new feature, the RGCN can already handle the relation prediction problem, and it can handle that in an inductive setting.
Yes. So the author conduct an experiment to show like how what is the added value of this mechanism compared to original RGCN.
Okay.
But the intuition here is that if we consider the normal RGCN, then we assume that we will have one hot encoder, one hot encoding embedding for each
I see
node.
they didn't elaborate the feature information, for example, the text information for those nodes. So that's why in this setting, it cannot re-handle the inductive setting, because for unseen node, it will, if it's unseen node, then we cannot create a new one hot encoding vector for that new entity, right?
Yes.
We have to kind of retrain everything by adding a new dimension to every entity.
Yes.
Yeah, but if we assume that we can leverage the text information of those entities, I think it can be naturally solved.
But they just trying to leverage different level of informations. So of course we can leverage the text related information, but by leverage the text information, the only added value is that, for example, the newly appeared node have the similar text information as some already observed node. Then we can assume that, okay, it will have the similar structure around it as this node. But actually, they do not consider any structure related information for this node. For example, this node is never observed in the training data. But in the text data, we know that, okay, it has like several link among the old data. So suppose in this graph, this 5 node is the old entity and this is the newly observed entity. And then we know that this newly observed entity can connect it with the old entity in this way. But if like in the but if we do not like encode this structure information correctly as the feature to represent this entity, actually we cannot leverage it.
For this part, I think
unless we retrain everything, right?
Not really. For graph neural network, it can automatically handle new node as long as we have the feature for that. So I think here the fundamental problem is like if we use one hot encoding, then it will not be inductive because that feature will not be generalizable to the new node. But if we use some like text one, It's like if we train everything, right? So then for that new node, we just leverage the trained parameter, then we can compute its embedding, and then we can do prediction related to that.
Yes, and then another understanding from me to this paper is that, so let us consider the scenario of these things. So of this scenario. So for example, if this is the training graph we can observe, and then by learning the embedding based on this training graph, actually we can encode the structure information into the embedding of each node. But when we're trying to handle some new node, actually, if we do not trying to retrain the whole graph, we can never encode the
so first of all, I agree
structure.
By using their method, then for any new node, right? So they can just leverage that one to those information to serve the purpose of the feature, and then it can make everything inductive. If we just pre-train the embedding for every word, right? So then that can also serve like similar purpose. But of course, the next question, like which one's better? For that one, I don't know. But I think for two cases, right? So either use this kind of structure encoding to get a feature for every node, or using the pre-trained text embedding to get a feature for every node. Both can handle this inductive setting.
Yes, but they're just trying to leverage different information. And then because like as like similar as the first paper, this paper, it will be also easy to include the text information by concat it with this structure information.
Right, that's true. And also another comment is like also inspired by this paper, because essentially we wanted to get a relative position of a node to that target node, right? So here it's just the shortest distance, which is just one possible way, and which is more natural for the homogeneous network. So for the heterogeneous network, I think a better way is like try to find the kind of shortest path. There could be multiple shortest paths, but for each path, right? So it's a sequence over relations. So if we have some good representation for those relations, which also can learn from pre-training or somewhere, right? So essentially, we try to transfer that sequence into embedding, because anyhow, right now, if they got 2, they just wanted to turn that 2 into one hot encoding, right? So essentially, they want to have some embedding. So if we can transfer that sequence of relations into embedding, if we have multiple shortest paths, we probably can do average, right? I don't know how we can do that, but it's kind of aggregation. So then we're going to get the embedding for that new node with respect to the first node in that target relation. Similarly, we can get another embedding with respect to the second node in that target relation, right? And that embedding, already embedding, and it captures more information, right? So probably that's will be more effective compared to just the shortest distance and this one hot kind of representation.
Yeah, I thought also, yes, it is. Yeah,
and also can directly, because shortest path or any path is corresponding to the body part of logic.
Yes.
So somehow, naturally, you can also, meantime, we can try to encode the body part of the logic.
Yes, I agree with you. Yeah. Because like here, we still like trying to assign the label by leverage only the shortest distance information. So this information just like can only contribute part of the information of the heterogeneous network. So it still like lost many informations. Yeah, maybe, yes. And then as we just discussed, So because like now what we're trying to handle is a heterogeneous graph, so we can no longer simply use the GNN to handle this scenario, because this scenario is like complicated compared to the first paper. Then the author proposed a new GNN architecture in order to adapt to this scenario. And then the design of the GNN architecture just following the idea of the neural message passing approach. As we know, the neural message passing approach will contain two steps. The first step is that it will trying to aggregate all its neighbors at the previous layer, at the previous layers. Then it will trying to combine its own embedding in previous layers with all its neighbors, and then to update its embeddings in the new layers. And then but here since we are trying to handle the multi-relation graph instead of the homogeneous graph, so we have to handle the multi-relation along the path. So in order to handle these kind of things, inspired by the RGCN, the aggregation function can be written in this way. So the idea is that for all the all relations in the knowledge graph, we will trying to find the neighbors of the target node T, and then we will use the we will first transfer its neighbor using a relation specific transformation matrix, and then to construct a new embeddings which can encode the relation specific informations. And then after that, we will also use attention to weight information coming from different neighbors. So here, this attention is learned for each specific neighbors, and then for each specific relations. And then in order to learn this attention, the formula is shown here. So the idea here is that because we would like to learn attention to weight information coming from different neighbors, and then as we know that this attention is trying to distinguish different neighbors regarding to different target nodes, and then connected by different relations. And then in this scenario, what we're trying to predict is that the target relation of the X and Y is RT here. So we know that this attention is related to all these four different informations. So we will concat the embedding of these four informations, and then we will learn. We will use neural network layer to learn a final softmax, a final sigmoid score of these attentions. But here, one thing we need to pay attention is that as we can see that we just use the signal gate here. So actually we do not normalize among all neighbors of a specific node. We just like trying to assign the score between 0 and 1 to indicate the importance of the information coming from different neighbors. And then here is like the aggregation step of the DRNL architecture. And then after that, after we aggregate all its neighbors and include the relation-specific method in the newly learned embeddings, we just trying to combine the information from the node embedding at the previous layer with the information aggregate from the neighborhood, and then update the embedding of the node. And then after that, we will, and finally, to obtain the score for the likelihood of the triple, we will concatenate 4 vectors in order to calculate the final score. So the first vector is the representation of the subgraph of the whole subgraph surrounding the target node. And then in order to achieve the embedding of the subgraph representation, we just trying to average all nodes embedding in this subgraph, and then use them to represent the whole subgraph. And then also we know that if we're trying to predict the score of the triple U RTV, then this score is related to node U, node V, and edge RT. So we will also concat these 3 embeddings in order to include the information from it. And then finally, we will calculate the score using linear layers like this. And then the training step will be just follow the common used the embedding training method. So we're just trying to calculate the score of the negative triple, and as well as the score of the positive triple. And then we're trying to ensure that the score of the positive triple can always be larger than the score of the negative triple. And then we can achieve our final models.
How do they get this subgraph level embedding?
You mean the HGL? So for the subgraph, so for example, the GCN will contain L layer, and then after the L layer propagation, we will get the embedding of each node in this subgraph. And then we just average all the nodes in this subgraph, and then they use the average embedding to represent the subgraph.
Okay, surrounding they just do a very simple average, kind of average.
Yes, just like the simple average.
Mm-hmm.
And then so finally will as we can observe, so during this GNN propagation, actually what we're trying to do is that we're trying to aggregate the information from all its neighbors in the subgraph, and then with the relation and then with the relation-specific transformation matrix to include the information, to include the relation-specific information, and then it naturally has the ability to mimic the node propagate to the target, the node in the extracted subgraph propagates to the target node step by step, following the guidance of different relations. And then we can see that actually the final embedding will encode all possible paths in this subgraph. So it naturally has the ability to learn the chain-like logical rule in this way. So here for the chain-like logical rule, it will corresponding to a path in the graph. So by encoding all the possible path information in this graph, finally this model has the ability to distinguish and then encode the path-related information, and then so it has like the ability to learn logical rules, and then it trying to finally it trying to compare their proposed method with some other logical rule learning method to show the performance of their method. And then they construct the inductive version of 3 standard benchmarks on 3 common use knowledge graph, and then in order to show the ability of their proposed model, they also sample the mutually exclusive subgraph of very variant size, and then they test the inductive version of the benchmark on different rule mining method, and then we can observe that their proposed method just achieved the state-of-art performance among all the rule learning method currently, and then it also compare the parameter used in their model with other rule mining method, and then we can see that compared to other rule learning method, their method just include very few parameters. And then another experiment is conducted to investigate the role of different components of their architectures, and then we can see that the enclosing subgraph and the no labeling schema is very important for their model. We can see that if we're trying to excluding these 2 mechanisms, the performance drop dramatically in the ablation study. So we can see that the power of the most of the power of the proposed method comes from the enclosing subgraph and the no labeling schema. And then that is like the basic idea of the paper.
So what does that V3 mean?
Sorry. Oh, here V1, V2, V3, and V4 is just 4 different versions of the inductive graph constructs based on the different data set. So they're just trying to show that their method is robust enough to handle different.
So it's not the hyperparameter H.
Oh, no, it is not a hyperparameter. It's just trying to show that we can create an inductive graph in different way. And then in all these different way, we can achieve consistent good performance.
Then do they provide this aberration study on H? Like how big? They just say that we definitely need to include that subgraph-based representation. Did they also provide the aberration study on like what it should be the size of that subgraph?
They do not provide the size of the subgraph because they just claim that when they're trying to construct the subgraph, they just use different size. So in this, so they just didn't care about the size. They're just trying to clarify that no matter how big is the graph, we can handle it correctly. Yeah.
Okay. And also for the rule mining, so they essentially, it's not really mine the rules, they just read the rules from the attention matrix, right?
Yes.
And then how do they compare the performance among different rule mining algorithms?
So basically the for the different rule mining algorithm, they're just trying to learn the attention for each different relation to indicate their importance at each different position of the body part. And then by leverage this attention. So for example,
how to read out. Yeah, my question is on
evaluation. How to read out. In this logical rule mining method, it will define an attention to indicate the importance of each relations at each step. And then they will also learn an attention to indicate the importance of each step. And then by multiply the importance of each step and each importance of each relations, we can for a specific relation, we can get a final score associated with it. Is this part clear?
Yeah, I think I'm clear readout, but I'm not clear how we can evaluate whether a soft rule is good or not.
For the neural LP and for the baseline method, they're trying to compare all these methods trying to evaluate the mine rule on the downstream task link prediction. So basically they just use the soft rule to predict the link. And then they use the performance of the link prediction to evaluate the quality of the rule indirectly. Yeah.
Okay, so the evaluation actually didn't really change. They're still doing this relation prediction, right? This rule mining, to me, is just a kind of provide some interpretation to their model.
Yes. Yes, the rule mining only so the difference of the rule mining method compared of their method is that the rule mining method has a way to read out and then to rank the logical rule and then give the explicit learn rule to the users, but their method is unable to read out those rules and then provide the explicit learn rule.
Now I remember like in one of our submissions, review asked us to compare with those rule mining methods, even we're doing large graph compilation or reasoning, or in other words, relation prediction. So do you think from this perspective, it's still reasonable to compare with those approaches?
Compare with the, so I'm not quite understanding.
Okay, so the question's like, do you remember like in one of our submissions, right? The reviewer asked us to compare with rule mining papers. Actually, we're not really doing rule mining, right? So we're trying to leverage the rule to enhance the performance. So then if rule mining are evaluated by link prediction, and we also evaluate our method by link prediction, do you think even our purpose are different, it's still reasonable to compare with those approaches?
From my opinion, I thought so. So first of all, many papers for rule learning trying to evaluate their method using the link prediction as the downstream task. And then I didn't saw the paper trying to just, for example, use the human to evaluate the learn rule or something like that. So until now, most of the experiment is still like based on some indirected evaluation, just trying to leverage the rule and then see whether the performance is good or not. So, but from my point of view, as long as the rule, as long as we learn the correct rule, the downstream task should increase. The performance of the downstream task should increase, right? So
I thought, if we are doing large graph compilation, it's indeed reasonable to compare with this rule mining algorithm.
Yes.
Okay.
Yes. Although our objective function is not for defined over the link prediction task, but as long as the rule is good, it will be good at,
Okay, great.
Yeah. So, and then also it is like a question like concerned me for a long time. So another reason is that all the existing works just trying to show their performance over the link prediction task. So it is hard to find another way rather than the link prediction. If we're trying to compare to other methods, that is like another concern. Yes, so if like we can come up with a better way, I think it is good, but it will be hard to compare to others.
Yeah, I think there are probably two directions. The first direction is like in Cheng's paper, right, Joey paper. So we can think of other tasks. For example, try to do like entity typing, right? Also kind of meta relation level reasoning. That's kind of without knowing some concrete entity, then we can somehow try to do reasoning at the meta level. So for example, what's the relation between a scientist and a university? Right?
I see. So we're just trying to avoid to incorporate too much entity-specific relation in the downstream task. So, sorry?
Yes, okay, yeah. Sorry, I just got a phone call.
Oh, yeah. So I think that is all about my today's presentation. So maybe we can finish earlier today.
Okay, sounds good to me. Thank you, Vivian.
Thank you. Thank you.
Thank you. Bye.
Bye.